welcome to today's colloquium. We have with us today Mike Wheatland, who is not visiting us, but is visiting Cora for about 3.5 months through mid-November on a sabbatical from the University of Sydney, where he also got his PhD in 1995. Afterwards, he spent a number of years at Stanford and then moved back to Sydney. Today he's going to talk to us about nonlinear force-free fields and coronal magnetic field model. So, Mike, please.
All right.
Whoops.
Okay. Thank you. Thank you, Alfred, for that introduction. And thanks to the people here at NCAR HAO for the opportunity to talk. So I am going to speak a little bit about modelling magnetic fields in the sun's corona using the nonlinear force-free model that I've worked with a little bit. Oh, thanks. Thank you, KD. Although, in fact, I'm going to focus on the application of that model to analytic boundary conditions and focus on some details of the model, the nature of the model, some interesting properties I think about it. And so this figure on this image on the first slide shows a calculation, a nonlinear force-free calculation from analytic boundary conditions, and I'll explain what is involved there. So what I'll do in detail is I'll give a motivation for modelling magnetic fields in the sun's corona and point out the popularity of this particular model, the nonlinear force-free model. Identify perhaps a couple of reasons for that. Then I'll go through the details of the model, really, the solar data that it is applied to, the vector-magnetogram data. I want to say very much about that. I'll speak then about the model and the boundary conditions for the model, which are important. I'll go through the details of a particular code, a method of solving the equations at hand that I've worked on, the CFID code. And I'll explain the details of that and then demonstrate it, show it applied to some analytic boundary conditions, one of which is the case that I showed on that first slide. And identify some properties of the solutions, and in particular the fact that with this numerical investigation for given boundary conditions, with the code you can find solutions, nonlinear force-free solutions, up to a maximum value of the energy of the fields that you're calculating. And so I'll say something about that. I'll also talk a little bit about the minimum energy state for the given boundary conditions, and identify something interesting about that I've been thinking about recently. Okay, so to motivate the work, why models magnetic fields in the sun's corona? Well, as I think people here know, the strong magnetic fields in and around sunspots on the sun power large-scale solar activity, in particular flares and coronal mass ejections. So that provides a motivation or something that you can point out, a reason for doing this. So more particularly, we'd like to understand and quantify the magnetic energy release that occurs in solar activity, and in principle we'd like to improve solar flare and space weather prediction, more generally space weather prediction, based on that understanding. So the nonlinear force-free model provides one approach, one model that can be used to represent the magnetic fields that are there in and around sunspots. It has become popular, so it is used quite widely now. So it's a model involving only a magnetic field that's not time dependent, so it's static, so it involves just the magnetic field B, so it's simple in that way. You can consider it as the simplest plausible model that contains free magnetic energy. You can justify it in a variety of ways, and people do. So in the sun's corona, at most locations, at most times, we expect that the plasma beta, the ratio of the plasma pressure to the magnetic energy density, should be small. So it's a magnetically dominated situation. And then if that the magnetic field in the corona is changing subject to flows that occur at the photosphere, the relatively dense photosphere, subject to slow flows there. And then we expect that the responses will be relatively rapid due to the large alphane speed in the corona, and so that you might then be able to consider it as a sort of quasi-static evolution, and the force-free model might be appropriate to describe the field at different stages. However, I mean, the different assumptions have been questioned, so I pointed out that just recently there was a paper by Hardy, Peter, and others questioning the value of the plasma beta in the solar corona. That's not a parameter that's well determined. The model itself then presents a boundary value problem for the magnetic field, but in fact there's an additional dependent variable in the problem that determines the values of the electric currents locally that are there in the field. So that's this alpha parameter that I'll explain in a moment. It's alpha is called the force-free parameter, or I will call it that. So the model's relatively simple in that way. Its simplest plausible model includes free energy, is what I've said. And then it would appear that we have the boundary conditions for the modelling from solar data. So vector magnetograms provide boundary conditions. Here's a montage of images that I put together in 2015, I think, for a talk at that stage, where what I did was I just looked in the literature for about in the solar literature for about the previous year and identified papers that used nonlinear force-free modelling applied to vector magnetogram data. And so these images just show magnetic field structures in the magnetic field for particular regions on the Sun. So the nonlinear force-free model has been used to reconstruct a coronal magnetic field based on boundary conditions in each case. And so all sorts of properties of the field are investigated in these papers. So down here, for example, the authors were looking at the topology, the connectivity of the coronal field that had been reconstructed in that way. So the different authors are listed down here for this. The point that I'm trying to make here, however, is that this method, the nonlinear force-free modelling from solar boundary data, is now frequently used. There are a few examples, and here is a very beautiful example, I think, of a reconstructed coronal magnetic field by my colleague Stuart Gilchrist, who is here. So Stuart is now at Cora NWRA, just over the way. And so this is from a paper by Stuart and Ji Zhao and others that's recently published. So this shows a nonlinear force-free model of for a particular active region, and this is using Stuart's code, which assumes historical geometry, so you can model larger regions on the Sun. All right, so I've mentioned this vector magnetogram data. I'll just say something briefly about that. I like this quote from a paper in 1996. Nobody can measure physical quantities of the solar atmosphere. So quite generally in astrophysics, so this is solar astrophysics, I would call it that. Quite generally in astrophysics, you're faced with this problem of remote observations of remote objects, and getting out the physical parameters at the source is always involves inversion, essentially. Well, the problem at hand, to determine values of the magnetic field, then for the data that I'm talking about, the vector magnetogram data, what's actually going on is that you have lines formed in the photosphere, around the photosphere, and the magnetic field imprints itself on those lines via the Zeeman effect. And so what's actually measured is for the instruments that give the most accurate values for the magnetic field. What's measured is the Stokes profile across the line, and then the process of taking those measurements and going to magnetic field values is called Stokes Inversion. So it involves modelling that Zeeman effect, and then also the having an atmospheric model and doing radiative transport through that. And so I'd say that it's an inference rather than a direct measurement. I'm not saying that the results are inaccurate. I'm just sort of identifying what's involved in this. There is also a 100 ambiguity in the direction of the field transverse to the line of sight, which needs to be resolved. So once you've done all that, what you have is a vector magnetogram. And it's a map of all three components of the magnetic field, the vector magnetic field, over a region on the photosphere. So that's what a vector magnetogram is. And so I've written it down here, the field here, Bx, By, Bz in local heliocentric coordinates, where Z is the direction perpendicular to the photosphere, so the local radial direction. There are now two space-based instruments providing high quality, high cadence data. So there is one on the Hinode satellite and also one on the Solar Variability Observatory, of course. And so the availability of this data is one reason for the popularity of the nonlinear force-free modelling. So the availability of vector magnetogram data has made this more popular. So that data provide boundary conditions for the model. Now the model itself, I'll say something about that. So the force-free model is the simple statement that the magnetic force, the Lorentz force, is zero, J cross B, where J is the electric current density, B is the magnetic field, and it is a magnetic field, so the divergence of B is zero. So J is the curl of B, is proportional to the curl of B. So that statement, J cross B equals zero, tells you that vector J is parallel to B, so you can write J as a local factor of proportionality, alpha times B. And so that introduces that force-free parameter alpha. So these two equations then tell you that the curl of B which is J, curl of B is alpha B, which is mu naught J. So the curl of B is alpha B. So this equation is the same as that one then, it's what we've identified. There's still this one here, which you can use. So if you take the divergence of this, then div curl is zero on the left-hand side. The divergence of alpha B on the right-hand side involves two terms, one of which is zero because div B is zero. So you use that second equation there. The other one is that B dot grad alpha is zero. And so this equation tells you that alpha doesn't change in the direction of B. In other words, alpha is a constant along the magnetic field lines. So that parameter alpha that's been introduced is a constant on the field lines. So from that little derivation that I talked through, it's evident that these two equations are equivalent to these two equations. So equations 2 and 3 are an alternative formulation of the model, and that's the form in which I'll show solutions of it, or that's the form that I use for the solutions I'll show. So what you have here with 2 and 3 then are four coupled partial differential equations. So 3 here for the vector B and 1 down here, the scalar equation. They're both nonlinear partial differential equations because here you've got the product of your two dependent variables, alpha B, and down here you've also essentially got a product of your dependent variables. So the model's simple, but it's also complicated in that way. It is nonlinear. Boundary conditions are important when you come to solve it, of course. So the boundary conditions for the problem in a half space, which is what I'll consider, so Z is greater than or equal to 0, are the normal component of the magnetic field in the boundary, Z equals 0, and the values of that force-free parameter alpha over one or other polarity of that normal component of B. So either over the region where Bz is positive or over the region where Bz is negative. So I'll call those the P and the N polarities, respectively. So you only require the values of alpha over one or other polarity because the alpha is constant along field lines. So the value at one foot point of a magnetic field line is mapped to the other foot point of the magnetic field line. So once you've specified the alpha at the positive polarity, for example, then that mapping gives you the value at the negative polarity. It's an interesting property of the model that is important. The vector magnetograms, however, provide you with your BZ values over a region on the Sun, which we're considering naively to be this boundary region for our half space. And then they also give you the Bx and the By over that whole region. So by differencing the transverse components using this equation, you can obtain alpha over the whole, over that photospheric plane. So the vector magnetograms then give you two complete sets of boundary values for your problem. So they give you the Bz and then they give you the alpha over both the P and over the N polarities. Now, if the boundary values are consistent with the model, then those two sets of boundary conditions will give you the same solution. But for vector magnetogram data, all bets are off, really. So, in principle, then, if you do your modelling from your P and your N polarities, choosing alpha from the P and the N polarities, you could get two quite different solutions. Okay. So I'm not going to really show that for the solar data, but that's true. That is what happens.
Excuse me, is the positive and negative polarity assumed balance in the domain
Yes.
at the surface, so every field line closes back?
Well, they don't have to close back. You can have open field lines, but you've then got to have equal flux for the open region. Yes.
Okay.
Yes, that is
So
assumed.
you do allow for that, but the flux coming through the surface is supposed to be
Yes.
absolutely net zero.
That's right. We assume div B is true, and it's a problem in the half space. Yep. Div B equals 0 is true. I left out equals 0.
But applying that to the Sun might be another issue.
For the data over a limited region, yes.
Yeah.
Okay, so I'll describe the code that I've worked on since 2007 now, I think, or 2006, which is called CFIT, so current field iteration. So it's an approach to solve those the nonlinear force-free equations that uses a method due to Grad and Rubin from a paper in 1958, where these two authors talked about the solution of the magnetohydrostatic problem more generally, which is a closely related problem. And they identified the boundary conditions for that problem which apply here. And for this simplification to the force-free problem are the ones that I just described. So the approach that's there in the code is as follows. There are two steps in, there's an iteration sequence to solve the equations, and there's two steps at each iteration. So this K index enumerates the iteration. And so what you do is at your iteration K, you assume you've got a magnetic field, B K minus 1, and then you solve this one of the two force-free equations that I wrote down by mapping your boundary values of alpha along your given field. So that's what you do, you solve that equation in that way. And that gives you the alpha values in your volume, the alpha K in the volume. So you've solved for that. Then you solve this equation, Ampere's law if you like, Ampere's law in the way that it's written down, where you've got your given field on the right hand side and you've got the alpha values in the volume that you just determined. So that gives you a current distribution or a current density distribution in your volume, and so you can solve that to obtain your magnetic field. You do this repeatedly, and then if you achieve a fixed point, that is that the alpha K is equal to alpha K minus 1, BK is equal to BK minus 1, then these equations are equivalent to the nonlinear equations. So you've solved the nonlinear equations if you do that. So the code's a Cartesian code. It works in this volume 0 to Lx, 0 to Ly, 0 to Lz as I've written it down. The boundary conditions the specification at each iteration of the Z component of the total field of the field in the boundary, Z equals 0, the lower boundary rather, and the alpha values at either of the two polarities, over either the p polarity or the n polarity, either where Bz is positive or where it's negative. Also, the boundary conditions for this finite volume, for this Cartesian volume, I'm going to talk about the case where the top boundary is closed, so the normal component of the field there is assumed to be 0. And the method of solution it assumes or imposes periodicity of the fields in x and y, so I use Fourier solutions. So they are the full boundary conditions for this code. Then the method of solution, in a little more detail, this equation 5 is just solved by field line tracing from all of the points in the volume, tracing back down to the lower boundary. And this second equation is solved by recasting, by introducing a vector potential and solving the vector Poisson equation. Using the Fourier transform method, so using 2D Fourier FFTs, so Fourier transforms in x and y. And finally, that iteration sequence, this iteration sequence is started with a potential field, again a Fourier solution potential field for the magnetic field in the volume. All right, so that's quite a lot of detail about it. But something else about it is the following: the way that you solve the equations is to decompose the field into a potential part plus a non-potential part. So you do this Helmholtz decomposition of representing the field as the gradient of a potential and the curl of a vector potential. So, and then the boundary conditions on those two components are the following. So for your potential part, the B naught, the Z component of that potential part matches the Z component, the normal component of the total field, on the lower boundary and on the top boundary. And then on the side boundaries, you've got the periodicity of the fields. That's the boundary condition. For the non-potential part, this BC, C stands for current there, at a given iteration. Then the boundary conditions on the field are that the normal component of the field is 0 on that lower boundary and on the top boundary, and thereby this sum of the fields, that together with this condition makes the total field match the required boundary conditions. And then also this field is solved using the Fourier method, so it's also periodic in x and y. So I'm going into some detail here because I'll come back to this. There's something interesting about it that I want to point out. So the code actually solves then the vector Poisson equation in this form for that vector potential, and it solves the Laplace's equation for that scalar potential find order. So here's something that's interesting, I think. This decomposition and these boundary conditions imply a version of the Thompson or the Dirichlet theorem, by which I mean that the energy of the total field, the integral of the square of the total field, is equal to the sum of the energies of the potential component and the non-potential component. So in this volume integral here, you've got the dot product terms, which you can rewrite as surface integral terms, and those terms vanish due to these boundary conditions. Which is what normally happens with the Thompson theorem. That's the way that it works. But here it's different because of this. You've got some different boundary conditions, and I'll come back to that point. But the important thing here is that what this means is that this potential magnetic field is a minimum energy field, in the sense that, if this term is 0, you've got the minimum energy for this. So if the EC is 0, you achieve your minimum energy, and it's that potential field energy. And that's achieved when you remove the currents in the volume, preserving these boundary conditions. So that's what that means. So that is a minimum energy field, and that simple theorem, that simple expression for the total energy applies. All right. So I'll show the application of the code to some analytic boundary data. I said I would do that. So we consider this. This little diagram down here shows the boundary conditions for BZ in the lower boundary and the boundary conditions for alpha. I'm going to use I've got to specify alpha on the P polarity, on the positive polarity. So for the magnetic field, I've got these little Gaussian spots, a plus, a spot here, a little region where the field's coming out, and a little region where the field's going back in. And then I've specified a small region at the center of this spot over here where alpha is non-zero. And I'll give it some value, alpha naught. So this is a very simple bipole configuration, current carrying bipole configuration that I'd like to solve for. There are my conditions.
So alpha is only non-zero for a point?
No, there's a number of points there. It's a fairly low resolution calculation. This is just to demonstrate it. You can do it for higher resolution, but this is just what I did for this talk. Yep. And then I've got a second set of boundary conditions that I'll just jump to show, just for comparison. And so it's the same configuration with the BZ, except now I've also put in a uniform bipole field that's in half the space on the left and half the space on the right, with the same sign. So the field in the background here is coming out and going back down here. Now, if you recall, I've got a closed top boundary, so all of the field here does indeed go back down over there. And then the alpha's the same. I've got a little spot of alpha with some value alpha naught at my positive pole there, positive spot.
That looks like it's not differentiable.
Not differentiable.
So
It's not. There's a discontinuity there, yes, but it's.
So there's no Bx or By across that.
No.
So
No.
there's no problem with alpha being undetermined there or something, right?
Alpha's zero there.
Right.
Yeah, I just specified that. But it's this is a numerical solution, so this is on a grid. And, yeah. All right. So what I'll do is I'll just show the iteration sequence then with the code and what you get for the two cases. So first of all, this is the case with just the bipole with no background field. So I think this movie will loop. So we're looking down on that volume again, and the yellow are a set of field lines that originate in this little the positive pole down here. The red field line is the one that starts in the middle of that positive pole in the center of the current. And then what's shown with this blue surface is they're the values of alpha once this thing achieves a fixed point, which it does. So once you've got a force-free and a good approximation to a force-free field in the volume. And so indeed you've got this, so that's an isocontour of alpha or whatever. You've got this, your alpha is going from one pole to, well, it's going from this positive pole where you specified it to a region over here which is not quite at the center of that other pole. So you end up with, for that value of the alpha naught, you end up with this distorted bipole configuration. So this movie shows the iteration sequence and achieving that fixed point where the field doesn't change after a certain number of iterations. So that illustrates that. And then for the other configuration with the background, then it's similar, but different. With that background, you find that you can achieve a more twisted field configuration. So in this case, you end up with quite a highly twisted bipole field configuration. But the same thing happens with the iteration sequence for this value of alpha. You do achieve a fixed point there with that. And so you can see the blue again is finally at the end shows you where the values of alpha are non-zero in that.
So that twist can be bigger because you've got unshown field lines there that have a tension force associated with them that holds everything down.
It does. So it's similar to the Titov-Demolan equilibrium, if you're familiar with that, which is a sort of semi-analytic equilibrium that's set up. But this is it, yeah. But you're right.
Okay. I was a little confused. I don't know if you'd mind going back to your boundary condition slide again.
Yep.
But the condition on the potential field at the top and the bottom, was something that I think I was drinking coffee or something at the time. I didn't quite get what that was. It looked a little, it didn't, yeah, so Z dot B0 matches Z dot BK.
The total field. Yep.
So
Matches-
what's that really saying about the magnetic field?
the potential field has normal component matching the total field at the bottom and at the top.
Total field at the top. What is this? I thought this was a closed boundary.
Yeah, so it's 0 at the top. I didn't write that in. But even if this was non-zero, yeah, even if it was non-zero at the top, I can also solve for that case. But I'm just focusing on the case where the top
Matches.
boundary is
What
closed.
do you mean by matches?
It's equal.
So if it's 0 at the top, isn't it 0 at the bottom?
No.
Okay, then I don't understand what this is, but maybe other people do.
Well, the field you've got field that goes
zero is the potential
Okay.
component. So BK is the sum of a potential component and a non-potential component. So what he's saying is that at z equals 0, the non-potential component has to be 0, at least in the vertical direction. And the same for
The current carrying part is only due to the horizontal components of the Z component doesn't contribute to the
So the
current.
currents are coming out of the surface.
They're only coming
only.
out. They're only coming.
There's no current in the surface. Is that what this is saying?
current in the surface.
Yes.
Yes, that's correct. Yes.
Okay. Then okay. Please carry on. I don't understand you.
These boundary conditions comes from the limitation of the observations or comes from something that you impose?
The limitations of the observations. This is how you solve the equations.
No, I know. I'm asking if these boundary conditions,
Which ones? The specifying the BZ
the one, yeah,
and the alpha on one polarity.
the ones talking about zeta.
Oh, this decomposition is just a way to solve those equations.
I'm talking about what you are talking about, the values in Z equals 0 and C in the top and then in the bottom.
Yeah.
My question is, these boundary conditions comes because you don't have these values in the observations?
Yes.
or-
Yeah. So that's right. We've only got boundary values at the bottom. So at the sides and the top, we have to do something. And so I've assumed a closed top and periodic sides.
So if you would have a variation of the magnetic field through the height, how can it affect to this?
This decomposition is the same, and it's as written down here, that the normal component for the potential part matches the normal component of the total field at the top.
But is that a choice, or is that something that is
You're-
somehow imposed by something else?
No, it's a choice. I'm assuming that all the currents close in the volume, if you like, in the computational volume.
Okay.
Otherwise, you really need those boundary conditions at the top that you don't have. So the hope is that you've got your volume large enough that you represent what's there close to the solar surface. Sorry for that extended. Okay, so I've shown the two movies then, and so let me just talk about these couple of general properties of the solutions. So, just by numerical experimentation, what you find then is that you achieve a fixed point for your iteration sequence for a range of values of alpha in the two cases up to some maximum value and correspondingly some maximum energy for your field. Okay, for larger values of the alpha, it doesn't converge. Or it doesn't, the iteration sequence, doesn't converge. It oscillates, essentially. The field oscillates. You saw a sort of oscillation in that evolution in the movies, and that doesn't die away.
Sorry, I have to ask.
Yep.
The low boundary, there is current going through the low boundary.
Yes.
Okay.
Okay, so you can achieve solutions up to some maximum value that I've called alpha max here. The energies of the solutions, or the free energy, the energy minus the potential field energy, increases as the square of the choice of your alpha. So here's a little diagram showing the log of the fractional free energy. So I've subtracted off the E naught here and divided by E naught, versus the value of alpha naught there. And so you see this very clear. The diamonds here are for the case without background field, just that simple bipole, And the triangles are the case with that, also with that uniform background field. The dashed lines are just trend lines for the alpha squared dependence, where I've taken just put an alpha squared line through the first point in the two cases, and the solid line I'll explain now. So that's a simple model. The solid line is a simple model to explain the alpha naught squared dependence. But first of all, the maximum free energies that are being achieved there, that the upper value of the energy is a small part of the potential field energy, so it's only a few percent in each case. I should point out here that the E naught is different in the two cases, so the E naught just depends on the BZ values, and they're different for your two cases. So that scaling, the scaling of the free energy with the square of your alpha value, or the square of your current, can be understood in terms of the self-induction of a little current loop. So modelling the currents that are there as a loop, or half a loop. And so for a toroidal current loop with a uniform current distribution, the energy is 1/2 Li squared from basic electromagnetism. And so that's the expression for the self-inductance L in terms of the major radius A of the loop and the minor radius, the size of your patch of current, or your current cross-section. R, and so the total current, the current in your loop just is proportional to alpha naught then in that way. So that's how you can obtain the total current from your boundary values, imposed boundary values. And so I drew those solid lines on the on the little diagram there. And so they provide provide an approximate representation of what's going on, but of course there's a crude representation of the currents that are actually there in the volume, so they don't provide an exact account of what's seen.
Is that saying that you've almost got a constant alpha linear problem here, or?
No, not at all. You've got a patch of alpha and zero outside. You couldn't get more.
Yeah, but within that
little
you're
region.
looking at the free energy, and so that's only where alpha is non-zero, and it's a stupid question, but I'm just wondering to what extent you get that scaling if you assume a linear force.
You get the same result with linear force-free fields. So I wrote a paper on that in
Okay.
this one here.
Yeah.
Yeah.
Okay. All right.
So if you increase your resolution, your model, you approach that.
You approach it. Increasing the resolution won't change those basic results. So there's still a limit.
Approach that solution, the
Oh, I don't think so. I think that the discrepancy is real. It's because that current distribution essentially in the volume is different from just circular lines of current
yeah, but
flowing.
that current is like a constant within the cross section, but then zero outside. It's like a sharp.
Yep.
Discontinuity there. But if you're increasing resolution, you think
I don't think I don't think that'll get those lines any closer. If what you're saying is, will that bring this solid line down close to this point?
No, dashed line is close to this.
Dash line.
Yeah.
Your solid line is the analytic solution. It's that.
Yeah, that's that crude solution with the current loop, solid
I thought
line.
it was an analytical solution. Yeah, which was.
1/2 Li squared is the solid line.
Yeah.
Okay, this is just a trend line where I just took the first point and put an alpha squared dependence through it. The reason I put that on is that what I expect to see is that as you make the currents very large, these points should lift off that line. Because the loop will start to distort, so your current paths become longer, that inductance becomes larger, so so there's a dependence then of that self-inductance on the current itself. So it's a nonlinear, which is the point that I was making down here. For large alpha naught or I expect a departure from that.
Okay.
And indeed, if you go back and plot I didn't show the figure, but if you plot that discrepancy, you can see that.
So that solution is actually not necessarily force-free. That solution, Li squared. And
No, that's just circuit theory. That's
Right, so
So
it's not
it's only
really
for
force-free.
in fact, it should only correspond for weak currents. You'd expect. where the field lines
Someone can-
don't change with the current. It's not perturbing the field. Yeah.
It's not, it's not force-free solution.
No. Yeah. There's nothing. Yeah. Okay. All right. So the maximum energy. That's interesting. The fact that there is that upper bound. Can we say anything about it? So J.J.R. Lee in a paper in 1984 showed that there is an upper bound to the energy for this problem, for the solution of the nonlinear force-free equations in a half space. And he obtained that from the Virial Theorem, the MHD Virial Theorem, which gives you an expression for the energy and the volume in terms of an integral over your boundary values for the field. So this integral involves the r here is in the vector in the plane z equals 0. So this picks out the bx and the by here. So this involves all three components of your field there. So that's the expression for the Virial Theorem. You can rewrite that in cylindrical coordinates, r and phi here in this way, where this is a little cylindrical area element. And then having done that, you can use the Cauchy-Schwarz inequality to rewrite your integral as the product of the square root of two integrals, which involve with integrands equal to the square of the two different parts in your integrand here, like that. So that's what Lee did. But this bound here still depends on all three components of the field, because this the BR here involves that's the radial direction in that z equals 0 plane. That involves the BX and the BY. But the net force on the coronal volume is 0 for the force-free model, and that gives you an integral constraint that's well known, which is that the square of well, bx squared plus by squared is equal to bz squared over that, in the integral of each. The integrals are equal, like that. So you can replace this one here, this br squared, by the integral bz squared, and then the right-hand side only depends on the bz distribution. Okay. So it's independent of bx and by. So that gives you this upper bound to the energy. I've rewritten it down here like this, as the product of square root of the product of two integrals, written down like this. So it depends only then on the bz and also on your coordinates x and y. So interestingly, it depends on your choice of origin. Okay. So Ali pointed out that it depends on that choice of origin and said to get the best possible bound, we have to take the infimum with respect to all possible O's. But if you just consider the dependence of that integral with the x and the y in it on the choice of origin, there it is written down for a general choice of origin, and it's straightforward to show that you get the minimum value by taking the x naught and the y naught equal to the bz squared weighted average values, like that. So it's easy to obtain that infimum value in that way. For those simple field distributions that I chose, then the x naught and the y naught are just the values in the middle, by symmetry. And so if you evaluate this, your I1 and your I2 then, which you can do easily, then the values you get out for that upper bound are large. So for the case of the bipole with no background, about 4 times the potential field energy. For the case with the background, about 6 times the potential field energy. So very large compared with the upper value for the nonlinear force-free solutions, the upper values for the nonlinear force-free solutions that I obtained, which were only a few percent, if you recall.
That's for the same bipole for points?
Same.
Bipole at the base?
Yeah, this one's for the one with no background.
Right.
Yeah, and this one's the one with the background. So yeah. It's for those BZ distributions. Yeah. All right. So that's an upper bound, but it's rather large. There's also the allosteric conjecture that people here will may be familiar with, and that is that the real upper bound for the energy of the nonlinear force-free field in the half-space problem is the energy of the open field, the so-called open field. And that's the field that you construct as follows. Here I've got this little simple bipole shown, the positive spot and the negative spot. You take the negative spot and make it positive, calculate the potential field for that field distribution in the boundary, which is, involves monopoles, of course, but you can calculate the potential field for that configuration, and it's open, all the field lines go in one direction, upwards. Then, for each point in the volume, you identify whether it's on a field line that connects to your spot, which was initially positive or negative. For the ones which connect to the points which were initially negative, you change the z direction of your field. So those field lines then connect back down to the boundary. So here I've drawn a little diagram where the red one's there. So this is an open field constructed in this way, where the red ones are the ones that are going upwards and the blue ones are the ones that are going downwards. So that produces this open field, and the conjecture by Ali and Starek, there were two papers that considered this conjecture that's the most energetic nonlinear force-free field, or force-free field. So it's actually a potential field. There's no current anywhere, but you've got a discontinuity, a surface of discontinuity between your field lines going in the two directions, which has a footprint down here, which is the neutral line between the two polarities. Okay, so that's interesting, but I don't think it's relevant for the calculations I'm doing for two reasons. One is that I've got a closed top boundary, and then the other reason is a little more subtle, and that's that the Arley-Sturrock energy for the periodic problem with the periodic boundary conditions I've assumed is infinite. Why? Well, this diagram kind of gives it away. Here, when you reverse the BZ values for your negative pole here, you've then got this flux distribution, which is all, it's this unbalanced flux distribution. If you just assume that the periodic side boundary conditions, then any unbalanced flux in the bottom has to leave the top. It can't leave the side because of the periodicity. Here, all of the flux is unbalanced. It all leaves the top. So every field line leaves the top, and so you can see that's what's happened here. And so I've done this calculation, relaxing the closed top boundary condition and calculating a potential field with that, doing this Arley-Sturrock construction. So all field lines then leave the top. So as you go up in height, the field just spreads out, and you'll just get a constant field value. And then as you integrate upwards, calculating your energy, you get an infinite energy. So there's an argument for that. All right. So I don't think that's relevant. It will be interesting, however, to calculate what that Arley-Sturrock value is, and I'm still trying to work out how to do that. But I'll do that for these cases.
So all the boundaries are current sheets.
All the boundaries are current sheets. There's a current sheet between those, the blue and the red field lines.
But also the current sheet at the boundaries, because you're using periodic boundaries. Right?
Yeah.
So they reverse sign, right?
Well, you've got. If you consider this extended, then you've got field lines. That's right, that are changing sign. Yeah, quite right. Okay, so what I get out of this is that, with these numerical experiments, you identify that there's a most energetic field, but it's not clear at all that you're getting close to that largest energy with the specific way that you're solving the equations. We don't know that, for example. So I haven't established very much there. Okay, there's also this question of the minimum energy, which I mentioned. So I mentioned that decomposition that's done by the code to solve the equations at hand has a little Thompson Theorem associated with it. You can also go back and do the regular field decomposition that's done to prove the Thompson Theorem. Separate your field into this then you consider the result from a CFIT calculation, one of these, and you separate your field into a potential part and a current carrying part. The gradient of the potential and the curl of the vector potential. But now, with the usual way this theorem's set up, the boundary conditions for your potential field are different. So the assumption is that your potential field has a normal component matching the total field on all boundaries, top and bottom, and also the side boundaries. Okay. And for this current carrying component, its normal component is 0 on all boundaries. So that's your usual, they're the usual assumptions. And subject to those, then the Thompson theorem follows. The energy of the total field is the energy of the potential field Bp plus the energy of the current carrying field Bj. And so from that, then, your potential field is the minimum energy field subject to these boundary conditions. Again, if you remove all of your currents from your volume, preserving these boundary conditions, then the field Bp results, it's the minimum energy field. So if you apply that decomposition to the result from the CFID code, then you have the two field decompositions. The one that I explained when I described the method the code uses, and that the one that's attached to the Thompson theorem, used to the Thompson theorem. So which one's the minimum energy? So you've got two minimum energies for your problem. The one associated the integral of the square of this field, B naught, or the integral of the square of Bp. Any guesses? How can you have two minimum energy? You can't. Well, one of them is less, isn't it? Okay, so you can show that the energy of this field is always less than or equal to the energy of that field. Okay, so there's no contradiction here. These two potential fields have got, are constructed with different boundary conditions. So, in particular for this one, for the Bp, the normal component of that field matches the normal component of the total field on all boundaries. So, with this one, the one that's used in the code, then you're only matching the normal component on the top boundary and on the top boundary and on the bottom boundary. So this is a stronger constraint on your field, if you like, with more freedom, and you allow more freedom in this case. You only require periodicity on the side boundaries for this field B naught. And correspondingly, that your minimum's a little bit lower in that case. So you've got to relax the constraints a bit. If that confuses you, then okay, yes. It is confusing, I think, but it's a fact. All right, so what I've done here is a little summary of nonlinear force-free fields and their use for modelling coronal magnetic fields, although I've focused on aspects of the model, really. So this model is used to reconstruct the coronal field with values from vector magnetograms. I introduced this code, CFID, this Cartesian nonlinear force-free code that uses the Grad-Rubin method. And it can be used for modelling solar data. I haven't really talked about that. I've talked about the application to analytic boundary conditions and sort of investigating some properties of solutions. And in particular, I looked at these analytic boundary conditions for bipolar fields and showed that you can obtain solutions up to a maximum energy corresponding to a maximum value of that force-free parameter alpha. And the energy scale is this, or the free energy scale is the square of alpha. There's an upper limit there, but the origin of that upper limit is not really clear. It's not clear. And then I talked about that basic field decomposition used by CFID and how it illustrates something interesting about Thompson's theorem and how the boundary conditions come into that theorem. Okay.
We already had quite a bit of discussion. There's a bit of time left though, so do we have any more questions, comments?
How important is it to have the full vector component? If you don't have the Bx or the By, you only have the radial field at B as z equals 0, how well can you do?
Well, you can only calculate the potential field,
Yeah.
essentially, unless you make some additional assumptions. Yeah.
So another basic question. When you do these models, or the people working on this are using basically photospheric magnetograms or vector magnetograms more precisely, and you are considering always the vertical component as constant in the photosphere. So my question is, how
Vertical
much?
component as constant. I did in my analytic ones. Is that what you mean? Or?
Constant height, you mean?
Yes, constant
Oh,
height.
yes.
Constant height, the vertical component is not changing. So my question is how much, if there could be any difference if you consider gradients in the photosphere, or even if you have information in the chromosphere.
Do you mean if you consider an irregular surface rather than
If you have a variation, even if it's linear variation of this vertical component of the magnetic field.
I don't really BZ, the BZ varies how?
So what he's saying is, if you have a boundary condition of not just the field strength, but also the gradient of the field.
Oh.
Or even if you have, because always in these models, no one is considering the magnetic field in the chromosphere.
Well,
And it's something that is like,
constraints. Yeah.
I know.
Yeah.
I mean, it's like,
No,
No, there are useful data now for the magnetic measurement determinations of the magnetic field in the chromosphere, typically the line of sight field. And I agree it would be useful to incorporate those in the modelling. So I have been thinking about that lately, but I haven't talked about it here.
just to know if it's something that is not important
Oh,
it's important, but we don't have the tools or what else.
No, I think it's important to think about how to use that data to improve the modelling that's done. Anything else?
Generally, yeah, there's so much of, there's so much that is difficult even with
Yeah, I know.
this, and then, but you want to add more constraints, but yet, boy,
Yeah.
doing it is gonna be.
Well, if you
I
have
was-
chromosphere data, that would be better. You just use the chromosphere. It's much more force-free than the photosphere.
And
So that's
Ah,
just my point.
But there are issues.
Yeah.
As I said, it's typically only the line of sight field. You typically don't have the vector field, and then also that is an irregular surface. We know that.
It's not on a constant.
It's not at a constant height.
What's your D,
Typically
is
the
it d tau for chromosphere versus photosphere?
But
I
even-
mean, the fluctuations that you can get.
Even as a first step, and for example, with SP data from Hinode, you can have a variation in the photosphere.
Yeah.
So
Oh, do you mean? Yeah, okay. I think
This
I
is the kind of
get.
stuff we're doing with
There are
the
inversions
yeah.
that get out
Yeah,
information on
exactly.
the field with height. So you
yes,
actually,
with
but
SDO
typically with
it's,
optical depth.
it's a little bit in the limit because
Yeah.
but with Hinode, absolutely, you can have this
I-
gradient through the atmosphere in the photosphere.
So I agree with you again.
So
That
I don't know.
it would be useful to think about, approaches to the problem that more generally approaches to the problem that incorporate those gradients. Okay, I understand what you're saying.
Yeah, I think there was a paper by Kyle Shriver and collaborators a couple years back where he was looking at how force-free is the photosphere, and the answer is it's really not force-free very much at all. And he was actually, I talked to him about it, and he was actually surprised by how non-force-free the photosphere appears to be. So yeah, I always wonder if this. So the photosphere is not force-free. We know that, and it's actually not that surprising. But you'd kind of think that in areas where maybe you're more concerned about it for, let's say, space weather predictions or things like that, the field is generally stronger. So presumably, it might be more force-free. I don't know if anybody wants to speculate on that. So I guess what I'm wondering is, we know that these models have their failings, and you can go and look at your HMI data, and you can go look at the nonlinear force-free field extrapolations that are available from HMI and compare that to the stuff you see in the AIA bands, for instance, and you can see that in a lot of places it doesn't really match very well. But does it match okay in the places where you're potentially more interested in this because that's where the energy is stored and that's where flares come from and things like that?
I would say that my experience with the modelling from the vector magnetogram data is you get better results when you've got these sort of really clearly defined current systems that are there, that are seen in the alpha values, and which are indeed the strong field structures typically, but they're not. Weak field regions, you don't get great results. If that's what you're asking.
Yeah.
But I haven't talked about that in this talk at all.
So is the upper limit to the energy that you're finding as simple as it's not simple, I know, but could one postulate that on the basis of MHD calculations, that this is just a dynamically unstable, I mean, a current-driven instability or something? I mean, it would seem...
Yeah, I mean, if you talk about the MHD stability, then you've got that zoo of instabilities.
Yes,
but they all, they tend to involve the plasma. You displace a plasma element, and then it keeps, the instability that keeps going.
Yeah.
And it's hard to relate that to the force-free. These are strictly force-free fields. If you just have a
well, you will get pinches and things here as well.
No.
Potentially.
Oh,
too.
well, so
I mean, current-driven instabilities are present, surely, in your calculations, are they?
there's no plasma here in the force-free model.
Well, but there is implicitly in the J.
If you consider just a 1D flux tube,
Yeah.
okay, the gold foil solution, you can have an arbitrary twist. That's a solution to the force-free equations. You just keep putting a larger value of alpha. It's also got infinite energy, of course.
Okay, because it doesn't have a degree of freedom to... It's so homogeneous that there's nothing you can do.
I mean, if you have a plasma column and you increase that current, it will kink, right?
Yeah, right, exactly.
You can get solutions, but they may not be stable if you let it dynamically evolve. But you
Yeah,
can get
yeah.
a solution.
Once you put a plasma in there. Yeah, but how's that related to this? Yeah, that's what you're talking about, right? If you get
I'm just saying your
MHD.
solution may not be a stable solution.
Once you put plasma in there, yes, it might just explode. And I mean, I think people find that when they try and take a force-free equilibrium from one of these codes and put it into a nonlinear MHD calculations. I think Stuart's been trying to do that, for example.
You can do a zero plasma beta solution, perturbation dynamic simulation of it. You can show that it is unstable, even if you don't consider plasma pressure. Just the perturbation of the magnetic energy, if you perturb it, you see that it is decreased.
Okay.
It doesn't require plasma beam.
All right.
Sure.
All right. I'll look into that.
It's possible though that the Grave-Rubin iteration, not being a physical evolution,
Right, it's
can
not a
arrive at
temporal
solutions that are
evolution.
unstable
Yeah, so you'll get.
physically.
Yeah.
All right, I think I'll close the discussion at that point. So thanks, Mike, again.